All right, let's get out those notes and let's finish up this last unit. Just looking at rational functions. Anybody need these? Anybody else need these notes? Okay, this is our last unit we got in this section. And I think this is a nice little mix-up, and it's pretty straightforward stuff. So we'll talk about rational functions. The key part about what a rational function is, we've been working with polynomials for quite some time now. I'm looking for my pen. So we've been working with polynomials for some time now. With these rational functions, we're going to look at what happens when we divide a polynomial by a separate polynomial. So this time we've got two polynomials, and we're going to divide the two of them, and that's going to change up and make some crazy things happen when we start looking at and analyzing graphs. Okay, so if we were dividing two polynomial functions, since this q of x, this function's at the bottom of a fraction, what do we know that this cannot come out to equal? Q of x cannot come out to equal what? 0. So our domain will consist of any values where q of x equals 0. So like it could be x equals 2, x equals 3. We might have to take those values out of our domain. And what ends up happening is these will be values where our graph is discontinuous. And we'll look at some of these ways where a graph can be discontinuous, but we got three main ways. This can create what we call holes in graphs, and I'll show you what that looks like in a second. It can create holes. We'll look at vertical asymptotes. And then we'll just have points of discontinuity. So our graph will be discontinuous. So points of discontinuity, or it'll be discontinuous in a few different ways. And we'll look at some examples of these. All right, so whenever we want to find a vertical asymptote, let's see, I'll look at a graph and we'll come back to this in a second. A vertical asymptote is, I'll just put a few graphs in my calculator. We'll come back to this in a second. A vertical asymptote is a vertical line that we don't see on our graph, but it's some vertical line where your graph will approach, but it will not cross it. So for instance, if we go back and look at this graph, right here we're saying that in this fraction, for those who can see it, on the bottom we have x minus 2. So basically, if x is 2, we would have to divide by 0. So in this function, x cannot be 2. So we got to take that out of our graph. And what happens is our graph breaks up where x equals 2. And as I go and approach it from the right, I see my graph is getting closer and closer to where x equals 2, but it won't cross where x equals 2 because x cannot equal 2 because my graph is undefined there. And so as far as close as I want to get to it, it'll just keep getting closer and closer to 2, but it won't cross. Same thing, as I kind of approach my graph from the left, it's doing the same thing from the left. It's getting closer and closer to where x equals 2, but it won't cross it. We call that a vertical asymptote. Does that make sense? And this is based on the denominator. All right, we get vertical asymptotes for any values of x that make the denominator equal 0. It's the same thing we've been doing when I say, oh, it has a fraction, set the denominator equal to 0, solve it. It's the same thing. We're just now looking at these and seeing what this does to the graph. It creates a vertical asymptote. Anybody got any questions on that? And we got two kind of points of discontinuity. One is a vertical asymptote. So we'll say asymptote as an answer to that. Okay, so you got two parts, two types. You have one where we have an asymptote that you can't remove and the factor will not cancel. But every once in a while, and we'll look at what this does to the graph in a second, you may get some point of discontinuity where it'll actually cancel out. So if I was looking at this graph right here, I would say that x can't be -2. But these are actually the same factors, so they can cancel out. When that happens, we don't really have a vertical asymptote. We have what's called a hole in our graph at this value where x equals -2. So just to be clear, we were able to cancel out the point that was discontinuous. When we do that, that will create a hole in our graph. And we get holes in our graph when a factor in the denominator cancels. And we'll look at all this in a second, and it'll just cancel. But we'll look at this in a second, but we'll be able to refer back to this in a little bit as we start to go. So that's the first kind of discontinuity. Any values that make the denominator equal 0, we call those vertical asymptotes. Those will be asymptotes that are up and down. Other type of asymptotes are horizontal asymptotes. Those are left to right. Okay, and these are based on a comparison of the degree of the top of our fraction to the degree of the bottom. Okay, and the way we think about this is what's happening as x gets bigger and bigger, and as x approaches either positive or negative infinity, depending on what side you're on. And the way we remember this is, so for instance, what's the degree of the top of this fraction right here? What's the degree of the bottom? So what you do is you ask yourself which one has the bigger booty. Does the top have the bigger booty, or does the bottom have the bigger booty? Which one has the bigger booty? Why y'all smiling? Oh, booty. I'm talking about treasure, like a pirate's treasure. Have y'all seen that popcorn where it's like pirate's booty? Like, man, what are y'all thinking about? I need to get y'all's mind out of good. I was talking about treasure. Which one's got the bigger treasure? I should have said that. But this is pirate's booty. That's what I was talking about, man. Y'all are something else, all right? All right, so you ask yourself, which one has the bigger booty? This one is, and we got 3 cases. One where the booty's bigger on top, one where the booty's bigger on the bottom, and then one where, what's the last case? The booties are equal in size. All right? Those are our 3 cases. To help you remember this, I like to name them as people. All right? All right, so the first one we call bow 2. This one is bigger on top, so the HA is U for undefined. What does that mean? That means there is no horizontal asymptote. That's our first case, bow 2. Bigger on top, undefined horizontal asymptote. Does that make sense? Why is this the case? Well, we ask ourselves which one's going to grow faster, which one's going to take control. As the number of x's, like the value of x that I put in, the top is going to grow a lot faster than the bottom. So what that means is when I divide the numbers, the top will just keep getting bigger and bigger. There is no limit as to what the top can approach. So I put this into Desmos Graphing Calculator, which is a free website. And if you ever need to go analyze some graphs, you can just Google Desmos Graphing Calculator. I know most of you have. And you can put these graphs in. But as I look at the graph, it doesn't have any horizontal asymptotes because there's no limit as to what x can get to. So there's nothing stopping me from traveling anywhere along this graph. Okay, so this is how the graph looks. Again, as I say, as the x values get bigger, it's going to grow faster, so your graph actually goes up, where in a bunch of different other cases, that won't be the case. But we call this one the bow 2, which means there is no horizontal asymptote. Our next case is bow both. Who's got the bigger booty in this case? What's the degree of the top? What's the degree of the bottom? So this one is bigger on bottom, and we have a horizontal asymptote at y equals 0. So Bobo, bigger on bottom, 0. Horizontal asymptote, and I like to abbreviate this, horizontal asymptote at y equals 0. This is the opposite of what we just looked at. As x gets bigger and bigger, the bottom will grow faster and faster. So what happens is the bottom will be a very big number and the top won't be as big. So what will happen is it'll be a fraction that gets closer and closer to 0. It'll approach 0. If you look at this graph, same graph, bigger booty on the bottom. As the values of x get bigger and bigger, the bottom will grow faster and faster, so the function approaches 0 as the values get bigger. And I go to the right. As I go to the left, the same thing happens. As the values of x get bigger and bigger in the negative direction, this graph just gets closer and closer to approaching 0. But it won't approach it because it's always numbers. The only way you could get 0 if you actually had 0, but it approaches the value of 0. Does that make sense? The bottom grows faster, so the graph gets closer and closer to 0. All right, and then our last case is where the booties are the same size. And so this one we say, anybody got any guesses? We call it bet C. Yep, bottom equal top. Any idea what's going to be the difference maker? C, which is you're right, 5 will be, C is for coefficients. You look at the leading coefficients. So the last case is bottom equals top. And if you want to write somewhere same booties, same size booties, you can. The deciding factor will be coefficients. I think I butchered that. But it's the leading number. Maybe put leading number. But we call this one Betsy. So the degree of the top is 2. The degree of the bottom is 2. So they're going to grow at the same rate. The difference maker and the number that it will approach will be based on the leading coefficients. All the other stuff that comes after, I mean, if we put in a value of 1 million, like multiplying by 9 ain't going to really have a difference. It's going to come down to the leading coefficient. So we would get our HA for this one at y equals the top coefficient 10 divided by the bottom coefficient 2. What's 10 divided by 2? So we would get a horizontal asymptote at 5, which is what we see on this graph. So this is what the graph looks like. We'll go around and kind of scroll through it so we can get a visual of that. All right, but when the bottom equals the top in terms of the powers, we use the coefficients to decide what's going to happen. So if we look at that one, the rest of the numbers, they just don't matter because the highest Greek term will have the biggest impact. And the other ones are just like small factors.
We're never going to have to like draw these out, right?
No, you don't have to graph these in our pre-calculus class. We just need to be able to identify these. Now, if you go to calculus next year or the year after, you'll probably start graphing these, but we just need to understand these graphs and be able to make sense of them. All right, so I put that graph in. We say that the coefficients will tell us where the horizontal asymptote is. And now, with the horizontal asymptote, there are certain cases where your graph may cross it, but with the horizontal asymptote, it's more of what is your graph approaching. So if we look at what's happening as we go to the left, this graph actually does cross where y equals 5, but as the values of x get bigger and bigger, it's approaching where y equals 5. Okay, so horizontal asymptotes are more about what is your graph approaching as the values get bigger. So I can scroll for as long as I have time, and it will just keep getting closer and closer to where y equals 5. Same thing as we go from to the left. as the value of x gets bigger and bigger in the negative direction, it's starting to approach where y equals 5. Okay, so that's where my horizontal asymptote is. I will have an imaginary line in both directions that my graph is approaching. All right, so we got our 3 cases. You compare the booties. We got BO2, undefined, no horizontal asymptote. We got BO, bigger on the bottom, where y equals 0 would be my horizontal asymptote. And then we got Betsy, where the booty on top equals the booty on the bottom. And it is the coefficients that are the deciders. You guys got any questions on those 3? All right, so this, I feel like once you start to remember those, man, this is like pretty straightforward. All right, so let's look at a couple of graphs, and we'll draw this graph, but it's more so about understanding where the asymptotes are. So just to give you an idea of what this will look like when you do this on test or on paper, you will just write what the asymptotes are. You won't have to graph it. When you do ALEKS, all you do is put the asymptotes on the graph. It'll have like 3 boxes, and you'll click, you'll decide, do you want a horizontal asymptote or do you want to place a vertical asymptote on your graph? You'll click the one you want and you'll just place them. And then that's all you'll do on these. So you won't have to graph these, but we do need to understand how the graphs will work. All right, so we'll do a little sketch of the graph, but it's more so understanding the asymptotes. So let's see, do we have any vertical asymptotes? So for vertical asymptotes, we set the denominator equal to 0 and we solve it. So let's set the denominator equal to 0. So for vertical asymptote, set denominator equal to 0, we get 2x squared plus 1 equals 0. Help me solve it. What would you do first? Subtract 1. Then what? Divide by 2. And then I do what to both sides? Square root. Can I take the square root of negative 1/2?
Wait, no.
I cannot take the square root of a negative number. Well, the question would be, that means that is there a number that would make the bottom equal 0? No. And if I think about it, any number I put in here, I'm going to square it, so it's always going to be positive. The only way this would be 0 if I can make it be negative 1 plus 1, but I can't make that happen. So there actually is no vertical asymptote. Does that make sense? Because I can use any value of x I want to. We tried to see what real numbers would make this true, and since we got to take the square root of a negative number, there is no real number that would make this true. This would be undefined, yes, meaning there's no real x value that I need to take out of my domain. I can use any value for x I want to, meaning there's no VA, no vertical asymptotes. Let's look at horizontal asymptotes. All right, so horizontal asymptotes, let's compare the booties. How do they compare? They're the same, right? Which case is that? Betsy. Bottom equals top. What are we going to use to determine where the coefficients? HA, this is Betsy. What's the top coefficient? What's the bottom? So we got an HA at 1/2. No VA, horizontal asymptote at y equals 1/2. Does that make sense? Let's look at this graph and then we'll do a little sketch of it to the best of our ability. So I think I put this one in. Yep, so this is that graph. Again, if we focus in on here, no horizontal asymptote. The way the graph just works, it goes up and it's starting to approach 1/2. So this is 1, this is 2, this is 3. Right here at 1/2, it starts to flatten out. and it's approaching 1/2, but it doesn't appear to cross it. Same thing here, it's approaching 1/2, but it's not crossing it. So we'll do a little sketch of that. And like I say, we want to just make sure we understand the horizontal asymptote. So we'll try to do a little asymptote at 1/2, and it won't be look like a Picasso piece of art, but we're doing the best we can. And then I'll come and just do that little V and just flatten it out. Yours look better than mine, or mine look pretty good? Yours probably looks better. Right, good with that?
Wait, I'm confused. The red line is the actual line, right?
The red line is the actual graph. The dotted line is the asymptote I put in there.
So since there's no VA, it'd be at 0, then you just go across the horizontal asymptote?
So vertical asymptotes are up and down.
Yeah.
So basically I don't have any break this way.
So you just go straight across.
Yeah, I do have a horizontal asymptote. So the graph won't go up over this line. It just kind of flattens out because it's approaching y equals 1/2. The red line is the actual graph.
Do we need to go over to our Alex thing, or do we have to do that too?
So when you do your Alex, you'll be putting in the dotted line, the asymptote.
Okay.
It'll say graph all vertical horizontal asymptotes.
Right.
You just be drawing the dotted line.
Okay.
All right, any other questions? Yes, sir.
I was gonna ask what I could use for that.
Okay, let's look at the next one. And we've already discovered that we got a hole, but we could do that same process. Sometimes you might need to factor it to see if any of your factors cancel, but as I look at this one, I see that I've got the same factors. So before that, I would need to know what value of x can't I put into this function. Well, I would take the denominator, and I would set it equal to 0. X plus 2 equals 0. When I subtract 2 from both sides, I see that x cannot be negative 2. So this is still a point that I cannot put into my function, even after I cancel it out, because I got that common factor of x plus 2. What I have left now will be y equals x plus 3 divided by 1, but I don't need to write divided by 1, it's just x plus 3. Okay, we canceled out the common factor of x plus 2. This is what I'm left with. Everybody okay? Okay, so now this is just a linear graph, but this is still true. X cannot be negative 2. I still can't put in there, because when I started, I couldn't put negative 2 into my function. So instead of a complete VA, this is just going to be a hole at x equals negative 2. So this linear graph, we can graph this without having to look at much. Where would I start graphing this one? So at 3, right? The y-intercept. And then how would I move based on the slope? I could go down 1, left 1. I could go up 1, right 1. But it's just going to be this straight line graph. But when I get to where x equals, so I'll go this way. And when I get to where x equals negative 2, I have a gap in my graph. And then it keeps going. So this is the hole in my graph where x equals negative 2. That's what a hole does. So if you look at this on the calculator, because all the space around it is in a hole, so it would look like a straight line, but if you went and looked at the table, what you would see is at negative 3 you get a number, at negative 2 you would get an ear. At negative 1 you get a number, at 0 you get a number, but you would get an error for this one because that value cannot be put into the function. That's what a hole looks like. Right? Got any questions? Let's graph one more and then we'll just find all the different pieces. Okay, so this one, got another fraction. Can I cancel anything out? The answer is no. I can't cancel out the x's or anything like that because these are together. Just make sure we understand that. So where do I have a VA at? x equals, well, I gotta add to both sides, so positive 2, right? Okay, VA at positive 2, let's graph that. Where x equals positive 2. And just to be clear, I'm graphing the asymptote. I use a dotted line when I graph the asymptote. Okay, how does the top compare to the bottom? Is it bigger? What makes you say it's bigger? The powers, right? So they equal? They equal? So who is this? Betsy. Betsy. So now we look at the coefficients. Bottom equals top, C for coefficients. This is Betsy. So we have an HA at y equals 1 divided by 1. Those are my leading coefficients, which is just 1. So we have a horizontal asymptote where y equals 1. Y equals 1 right here. I'll just do a dashed line to show that that is my horizontal asymptote. All right, and now we got a bunch of different things going on. So what's going to happen is it looks like my graph is going to be stuck in some of these corners. Let's go look at it. Everybody okay with the asymptotes we drew?
So 1 over 1, so you do it with the leading coefficient?
Yes, just the leading coefficients.
Oh, okay.
Yeah, because x here and x here, if I put in 100 for x here, I also put it in here. And my values, they'll be pretty much the same. What'll be the difference maker is the leading coefficient, how much I multiply them by. All right, so let's look at this one. Nope. So that's my whole. Obviously, you don't see the whole. Then if I go to this one. All right, so if we look at this one, we had one asymptote at x equals, y equals 1, right? That's this one right here. And it's starting to approach 1, but it's not going to cross it. Same thing this way. This is 2. It's starting to approach 1. It's not going to cross it. And then our vertical asymptote was at x equals 2. That's this one. So if I zoom out, you can see how the graph starts to equal that. So our asymptotes were like this. Does that make sense? Does that make sense? So we're going to graph 1 over here that's kind of stuck, and then 1 in the bottom left that's stuck as well. So we had 1 in the top left that was curving in, couldn't get out, it was stuck with the asymptotes, and then we had 1 in the bottom left, top right and bottom left. That's my graph. Got any questions? All right, let's work on just finding some of these to finish up. So let's go down to the bottom. We run out of time, but it's the same thing, guys. Just some more problems. You guys, let's identify the horizontal asymptotes. Make sure as you start to work these, you just identify what it is you want to find. And let's just label these. What's bigger on this one? They're the same, so it's Betsy. So we have an HA at 2. Good job. 2 over 1, so at 2. What about this one? Bottom. Bigger on bottom. Who is this? Bigger on bottom. 0. HA at y equals 0. Who's this? Top's bigger, so who is this? Both 2? Bigger on top, undefined. No HA. What about this one? Bigger on top. Who is that? Both 2. Figure on top, undefined. No horizontal asymptote. Last one here. They equal. So this is Betsy. So what is the horizontal asymptote? Good job. Top coefficient is 1. Bottom is -2. HA at -1/2. This is easy, right?
Why is, the second one, why, yeah,
This one?
yeah.
Because the bottom is growing faster and the number is going to be bigger on the bottom. So your graph is going to get closer to 0
So it was just a 0
every time
for the, that one or the.
for this one. Anytime it's Bobo,
Uh-huh.
the bottom's bigger, it's always just a 0
Okay.
every time. All right, and then we can find the VAs. You just set it equal to 0 and you solve. You guys got any questions? All right, so next week you got Alice on this. All you do is place in the asymptotes. It might take you 10 minutes or so. If you don't finish this weekend, you should have some time on Tuesday where we'll do our test review and get ready for our test that we will take on.
Is it on Wednesday or Friday? Or is it the-
We can do it on Friday, but we'll
Wait, no,
do a
is
new
it-
lesson on
Is
it.
it an 8? Oh, it's 8 weekend.
It's an 8-day. We'll do it on Friday. Yep, the 3rd.
Oh, it's on practice.
That's what I was gonna ask. Some people like to do work in class, but some people like to play something.
You wanna do both?
We can do both. Let people who wanna work, and then we can play trash the ball. I wanna play trash the ball though? Alright, so I'll set up that.
Debbie Jackson.
I'll set that up.
No, Debbie Jackson.
Jackson needs to work on his sportsmanship, what'd you say?
Yeah, we have to get a little.
Humbling?
You need some humbling.
Yeah. So he ain't listening to none of it. Hey, are you hearing any of this, Jackson?
Jackson needs to be humble.
He said he's not hearing none of this. He is not going forward. Jackson, they said you better practice over the weekend. They said you're going down.